Perfect. Please, over to you, Onur.
All right, thank you. Welcome again, everyone. Today's presentation is going to be about automated detection of pyroclastic density currents using seismic and sound or infrasound sensor. This is going to be given by me, Chris. And I'm going to talk about, I'm going to give you a short brief about Volcano with that project and what a pyroclastic density current is. We will talk about aim of the automated detection and acoustic signature of the volcanoes. I'm going to give you some literature on this. And the explosion analysis, that also means what we are trying to detect. And our device specifications, like microcontroller and sensors that we've chosen, a detection algorithm, some future work, and then we will have a Q&A session in the end. So Volcano with that project is initially me, Paul, and Emin started to work for, which is aimed to obtain some high-resolution data from the dense core of moving pyroclastic density currents, also called PDCs. And how we're going to do it is we're going to deploy some custom-built X3 Ku band radar systems at the San Tiaguito volcano in Guatemala. And at the right-hand side, you can see where the volcano on the map is, which is quite far from here. And what's a PDC? To be honest, as an electronics engineer, before I started to work for this project, I had no idea about PDC. That's why I thought it may be better to give some brief explanation of PDC. So, in general, volcanic eruptions can be divided into three patterns. One is the lava fountains. By the way, the picture right-hand side is the picture taken from the San Tiaguito volcano, which we are going to work on during an eruption. And the first pattern is the lava fountains, which are the lava spread to the sky after the explosion. And the second pattern is the lava and tephra fallout. And the third and most important one is the pyroclastic density currents, also called. These are the lava flowing through the ground due to the gravitational force. And they're quite fast, with an average speed of 100 kilometers per hour. They can reach up to 700 kilometers, according to the picture. And they are the most dangerous and most important part of the volcanic eruption. And what is the aim of this detection is we are trying to develop and improve existing algorithms for the automated detection of PDCs using some seismic and infrasound sensors. Infrasound means here inaudible acoustic waves below 20 hertz. And why we are doing this is we don't want our radar to working 24/7, which is quite energy consuming because we are relying on batteries and solar power there, and also recording getting radar image for no eruption is going to be memory consuming. And what we are trying to detect is there are some examples of time domain of the explosion sounds, and the image B here, the graph B here, is from our volcano again. And as you can obviously see, in time domain, explosions showing some similar characteristics. And in frequency spectrum, explosions, volcanic explosions, tend to generate acoustic waves with a broad frequency spectrum. And the most common way to detect these eruptions are focusing on the infrasound waves, which are between 0 to 20 hertz. And our initial question was what about the sound that we can hear? What about above 20 hertz? Then I done some FFT analysis on MATLAB using the explosion sounds that I found on the internet from different volcanoes. And I applied a broad range of FFT to see the frequency waves, the power waves on the signal. And as we can see, there's an accumulation roughly 100 hertz frequencies. And within a more narrow FFT, we can see that there are also some audible noises accumulated roughly between 50 to 100 hertz. Then there are some questions about the assumptions that we made. First is are the data that I've used, are the recordings that I found on the internet are reliable? The answer is probably not, but we're planning to collect some more data because we don't know how were they recorded. We don't know the distance between the volcano and the microphone. We don't know what kind of microphones did they use. We don't know if they put any effects on them or not. So we don't know which type of data we are using. And we are planning to collect some more in the field probably in this May, and if there is still some energy between the audible part of the explosion, can we detect them using a microphone? This is the other question. And can we create a flexible detection algorithm to adopt different frequencies for both infrasound and audible waves? So this is the third question that we are searching for an answer. And in 2006, this is I think the most comprehensive study about the volcano detection, which is also quite old, from Harvard University. They deployed a neural network to the volcano, and how it basically works is when earthquake and eruption occurs, the nodes detects the seismic event and sends the event to the base station, and they're using an exponential weighted moving averages algorithm over the input signal with two input signal with different gains, and when the ratio between two signals exists thresholds, the node says there's a seismic event there, and if the base station receives signals from more than 30% of active nodes within a 10 seconds window, it decides that there's an eruption, there's a seismic event. It has zero false detection, but it has a lot of missed events. And the new works are mostly based on new methods like machine learning, some satellite-derived observations, lightning inspections, etc. Because they say the single source infrasound recording, like what we are going to do, is a limiting factor for more sophisticated algorithms. And now it's easy to reach a lot of data collected from the network of seismic stations. But in our situation, we are planning to do it on-site without a base station. So that's why we still go for the acoustic wave analysis. So what we can contribute with the new design is the previous ones are mostly big devices. They consume power and they're difficult to deploy. They need a lot of maintenance and else. And in our case, we don't need any wireless or wired communication between the devices, and we don't also need a base station because we are planning to do the detection on site within the device, and then decision maker is also the device itself. So we don't need a sensor network, means we don't need a GPS to localize each sensor to know if the nodes are sensing the eruption are close or not, like the previous literature examples. And our sampling rate is quite all right. It can go up to 10 Ks, but we are, for the FFT, we are using 1 kilohertz of sampling rate, but for the seismic detection, for the vibration detection, it's all up to the loop speed of the Arduino, which is quite high. And we can increase the robustness and the detection accuracy, and also leaving a device on the volcano side adds some risk mitigation because there's no human needed to use it. And as a microcontroller, after some discussions, we started on Arduino Uno because it's quite power efficient with enough sampling speed. Then we had some memory issues while dealing with the FFT, then jumped to the Arduino Nano. And we're planning to change the microcontroller again, which I'm going to mention on the future work as well, because we are planning to place IoT interface with a new Arduino IoT board. As a geophone, we are using a geophone which has a natural frequency of 4.5 Hz. Natural frequency for the geophone means the frequency that geophone can sense the frequencies above it. So lower natural frequency means better frequency detection, and the one that we are using has quite low natural frequency. And we are also using omnidirectional microphone for the signal within the frequency range, like 20 up to 20 Hz to 20 kilohertz. But the microphone also still needs to be upgraded in the new one because we are using a chip one that we got from DRS. And our device basically going to be a 24/7 on-duty Arduino, will drive both geophone and microphone. And when device senses the volcanic activity, output will trigger rest of the system, radar, the computer, everything, maybe a 3G modem, everything, for a certain amount of time that we set. It can be 6 minutes. And we are planning to wake the rest of the system up with the LAN port to develop communication within the computer and Arduino using a LAN chip for Arduino. Then, after the time, the output will be low, and all the other systems, except the Arduino, except the watchdog itself, are going to be back to the standby state till the next figure. And here we have some op-amp circuits for our transducers. So for the microphone circuits, we use a inverting op-amp circuit, which has a logarithmic potentiometer there, which makes it quite flexible and which gives us the chance of adjust the gain. So it still can be used with different devices. And as we don't know how low the signal is going to be, it can also reduce the possibility of the saturation due to the load explosion signal. And here, another point is we are using a potential divider, which gives an offset of half of the Arduino supply voltage, just to minimize the possibility of clipping on the input signal. And here is the gain of the op-amp circuits with green one, the one on top is the gain on with a frequency sweep when the potentiometer is 100%, set 100%, and the red line, red curve is the gain again when the potentiometer is low at 5%. So we have adjustable gain between 15 to 50 dB roughly. And here's our geophone circuit. It also has the similar specs with the microphone circuit, except it doesn't have a pot this time. And the geophone circuit has a bit lower gain compared to microphone circuit because it is tend to saturate easily when the vibration gets higher. And our first approach for the detection mechanism, it was actually Paul's idea, and it was a really nice idea, is applying a digital filtering to the signal that we are receiving. What we have done firstly is as you can see there, the input signal is a signal with an DC offset, and we applied simple low-pass filter, method on it, which is adding the delayed version of the signal, like small proportion of the delayed version of the signal to the signal itself. And omega 1 here, omega 1 t here, omega 1 is like 2 pi and 1 hertz in this particular example, and t is related to the, again, cycle time of the Arduino, and which is the k of the filter as well. And then by extracting from the VDC, which is 512 here, like half of the Arduino's ADC range, will give us a high-pass filter. So then we can get rid of the DC component of the signal. And we applied another low-pass filter with 50 Hz corner frequency. And here, omega 2 is 2 pi 50, and t is again Arduino's sampling speed. And then we got a detector here, which rectifies the signal basically. And we applied a post-detection delay, which is the time that we expect to see a signal within this frequency range. And if finally the signal is higher than the threshold, it triggers the output. It works quite nice, actually, and the response at 50 Hz is roughly 3 dB, which is quite nice. And at 500 Hz is around minus 18 dB, which should be 20, but still all right. I mean, there's some mismatching between the ideal filter response and the response that we got from Arduino, as expected. Like, there can be many reasons for that. We can also add some of these effects to the filter response instead of using an ideal filter response. But like overall, it works nice, but we need something more sophisticated. So we decided to have a detection algorithm which user can set the vibration threshold, the delay time between the vibration and the sound, because we are expecting the ground to conduct the waves a bit faster than the air. So the vibration should reach the device before the sound comes. That's why we wanted to add a delay between vibration and sound. And user also can set sampling frequency and the number of samples of the FFT and the frequency band of interest, so which frequency range that we are looking for, and the power threshold across the band, and the time that device calculates the average power along. So all these variables should be set by the user according to our detection algorithm. And how it's going to work is geophone scans the vibrations continuously, and as soon as it detects the seismic movement, it makes the microphone turn on, and the microphone digitizes the sound that it hears. And finally, if the mean power across the frequency band is higher than the threshold along a percent time, and if it is enough gap, enough delay between vibration and sound signals, Arduino will give basically a digital high. And for more understandable approach, we have a flowchart here. Here is, sorry, I need the pointer again. Okay, wait, can I use the pointer and the magnet at the same time? No, probably. Anyway, so here's our start point. The device digitizes the geophone signal continuously and checks if the vibration is higher than threshold or not. If it's not higher than threshold, it continues to do the same loop. But if it's higher than the threshold, the input switches on and digitizes the signal for 1 second in our test setup. And before taking the FFT of the signal, we apply zero metering to get rid of the DC offset. And then after taking the FFT, we apply the band pass filtering and calculate the average power, average mean power actually across the band during the time that user set. And if the power is higher than the threshold, there's another decision block, but if it's not higher than the threshold, it goes back to the initial states to check the vibration again. But if it's higher than the threshold, another decision block is if there's enough time gap between the vibration and the sound. If it is enough time, if the time is higher than the user sets or equal to the user set, we will give the digital high, the output, and this output will be high during the time which is also defined by the user. All right. Sorry. Then I would like to show you how it works. If I can. There you go. Now here, like I split the screen to the three parts. Left-hand side, I know it's quite hard to read, but sorry about that. There's no magnifier for the video. At the left-hand side, the COM port of the computer, which we get data from Arduino, and the middle screen is the device itself. So it's the prototype. You can see the geophone and the microphone on the board, and two op-amp circuits with a pot on one of them. And at the right-hand side, there's a pure like sinusoidal sound wave that I found on YouTube. So, like in this particular example, I'll try to demonstrate how the device works. As you can see on the communication port, like the device continuously reads the geophone value, and as soon as I give a vibration by like putting my hand to the desk, we get the message. By the way, it's just for demonstration. It slows down the Arduino speed, sampling speed, so we're not going to use it on site, but just to demonstrate like how the device is working, I just write that code for just to show off. So it shows the vibration detected and it gives the detection time. And in this setup, we are seeking for the frequencies from 0 to 200 Hertz. And the capturing time that I set is 3 seconds. So the device listens to the environment for 3 seconds and then says the power threshold of a number, which is meaningless here because we can't calibrate the device. So, but we know what we hear. So I put a threshold of 3 million of something. But since there's no signal, it's not exist again. I give another vibration, listens, and threshold hasn't been exceed. And I switched on the video, which I get 100 Hertz sine wave to my computer speaker, and then I give the vibration there, so the red LED flashes, and now the power threshold is exceeded, and it checks if the time delay between the vibration and the sound is exceeded as well. I put just 1 microsecond just to check if the code is working or not. Then I put 10 seconds of digital high if all the conditions are working. So after 10 seconds, it should get back to the initial state, which is checking the geophone value, and it does basically. So the prototype for the device is working as expected. And like as a summary, what I've done so far is a literature review, and I've done some time domain and frequency domain explosion analysis. And we decided the microcontroller and sensors that we are going to use. Also, the amplifying circuits for both microphone or geophone designed, simulated and fabricated, so we are using them. And we discussed the triggering methods, and the final decision is you're doing it through LAN port, so we need to develop a communication method between the computer, which the radar is going to be connected, and the Arduino. And we also developed the detection algorithm, which is quite flexible. And we've done a prototype for testing. And for the near future, the very first thing that we're going to do is a small size PCB for the device. And in the final stage, we are planning to bury the geophone underground, and we are planning to leave the microphones or like infrasound voice wave sensors on the circuit within a weatherproof case. And we are planning to place a keypad and an LCD screen to calibrate the device set the values on site without a computer needed. And we're planning to improve detection methods as long as we are getting more experience and more data to characterize the eruption. But luckily, we can apply the frequency and power approach to the different signals, data that we get. So we can adopt some other sensors to the device just to make more precise detections. And we are planning to use IoT interface to remote control the Arduino, just to check its states and just to be able to trigger the radar even if there's no eruption. We want to trigger it remotely, like from here or somewhere else in the world. And here are some bibliography. And this is the end of the presentation today. I'm happy to answer the questions if you have any.